So then with this recording, you can go back and check some details about the software if you can't remember it. Okay, and also please feel free to stop me and ask questions. That's sort of also the main thing I would like you to do, is to clarify your doubts at this point. Don't just sit there. If you're not following anything, just ask. There's no harm in asking. I'm not going to get mad or if you ask me some very basic question at this stage. It's fine. Clear from the exam, it's very clear that many of you have not understood some very, very basic things. So please ask questions so that I can explain it. Okay, so I'm going to share my screen. Sorry, just give me 1 minute. Okay, Panya, can you see the screen and hear me?
Yes, no, I can hear you, and the screen is also visible. Hello?
Yeah.
So we can hear you. And the
Okay. Sorry, I couldn't hear your voice clearly because some speech going on in the background. Okay, so this is the first problem. And, again, this was a very basic thing which we had done in class. So I will use this circuit to also revisit some of the basic concepts. See, the most thing which I had actually in the last discussion I had mentioned, many of you had made a mistake, is just even setting up a basic reflection coefficient measurement. And the thing is, the reflection coefficient is pretty much the only thing one can measure in a microwave circuit, right? That's the most elementary measurement, and that's pretty much the only thing you can measure. All other quantities are sort of derived from the reflection coefficient. So this problem asked you to set up a quarter wave transformer at the frequency 6 gigahertz to match a 50 ohm port to a 20 ohm load. So how does one do that? Right. So you create a schematic. We are making an impedance transformer, so we need a section of transmission line. And we know that, and it's also given, it's a quarter wave transformer, which means lambda by 4, or in electrical length, it means 90 degrees. So we go to the elements, go to transmission lines, coaxial, and the electrical version. This is the simplest transmission line, which is what we have been using for most. The frequency is given, so you set this up at 6 gigahertz. The characteristic impedance of the transmission line section is what one needs to compute. And then you put your standard port. So it says that you're trying to match a 50 ohm port, which is what this is, to a 20 ohm load. So the load is present in the lumped element under resistor. So we can use this load here, which is just nothing but a resistive termination. The one here which is called resistor is equivalent. It's the same thing. You just have to put a ground here. This one comes with a ground connection by default. There is really no difference from the perspective of this measurement. Okay, so we'll just stick to this load, and you have to put this to 20 ohms. Okay, so all the parameters given in the problem: 50 ohm port, 90 degrees at 6 gigahertz, and this is what we have to tune now, the 50 ohm transmission line impedance, which is the default value, and then it's connected to the 20 ohm port here. Okay, so at this point we need to set up the measurement, and that measurement is essentially the reflection coefficient measured from this port, because what we are trying to do is to see whether we can couple power from this 50 ohm port into the 20 ohm load resistance. So if this section of transmission line was not there, so in fact, let's remove that for a moment, and then we'll start from that reference point. This is not a match situation, right? So you know that 50 ohm port will not match to a 20 ohm, so there'll be some reflection. So that's what we want to measure. So we go to graphs, create a new graph, and you always use a rectangular graph for all our measurements. And then under graph, you say add measurements. Okay, so this is where a lot of the mistake happened. And again, I don't know why, because at least in this software, the dB is not selected by default. So I'm not sure what happened in many of the cases. And the default measurement it opens up also is the scattering measurement, which is S11. Since in this case, there is only one port, S11 is the only thing you can measure. And that is the same as the reflection coefficient gamma, right? So what gamma are we talking about here? Right, this is the same gamma, which is for a simple case of just a load and a port is just Z minus Z0 over Z plus Z0. Right? This is, we had looked at this early in the class, where Z is now the load impedance, Z0 is the port impedance, and this is what is the reflection coefficient. So this is the full complex reflection coefficient formula. If Z, Z0 are written as complex numbers, depending on the situation. This particular problem right now, everything is just real, right? The port impedance is 50 ohms real, and the load impedance is also 50 ohms real. And you see when these two are equal, then gamma is 0. That means no reflection, which means perfect matching. Now, of course, all of these quantities can be frequency dependent, in which case you can have gamma of omega, which is a function of frequency. Otherwise, if there is no frequency dependence, then it's basically not going to show any variation with frequency. So this is another thing you have to keep in mind, that implicitly, pretty much when we define any measurement, there is a different value at all frequencies, unless the elements you're using are themselves frequency independent. So for example, right now, what we have set up is just a simple port and a load, right? Let me just close this for a second, go back here. This port here is 50 ohms at all frequencies. This load is 20 ohms at all frequencies. That's what the definition is, right? This is not in practice for any system, but in this circuit, that's what this means. There is no frequency dependence in these terms. The frequency dependence will come the moment we introduce this transmission line section into the system. Because this, of course, has a specific length, electrical length at a particular frequency. So it's the amount of phase it accumulates as waves travel back and forth will depend on what frequency you're transmitting through this system. Okay, so go back to the graph, add measurement. It's always a good practice to choose the correct schematic here. And in fact, it's also good practice to name the schematic, because you start using it and suddenly everything is schematic 1, 2, and we don't know what's going on. So we'll call this, let's see, quarter wave transformer. And single section, since we have to later on make a double section one. Okay. Go back here. By default, the data source. So this is the schematic from where the data is coming. It could be, there could be other kinds of data sources, but we have not covered that. So you choose the correct one. You look at, so this port parameter is also, in case you get lost here, just to remind you, these are the different sections. Almost pretty much we have done is in the linear section. In the exam problem 2, I had given one example of nonlinear one, which I will go through after the first problem. But otherwise, pretty much everything is in it in this linear one. And even under linear, you go to port parameters, which are the scattering and other types of parameters which are here. And there also you just choose S. So this is the default setting anyway, and this is what comes. And by default, you have this complex modifier here. Okay. Now, what does this complex modifier mean? Remember, I told you that gamma is a complex number in general. So this tells you what you want to plot, because you cannot plot a complex number by default, right, on a 2D standard 2D graph. So you can choose the real part, the imaginary part, the magnitude in dB, and this is the only setting where dB can be enabled. Okay. For it does not make sense for any of the other settings. You cannot have real and dB. I mean, I guess this should have been disabled in the software, but there is no log of quantities when you have things which going from positive to negative, because real and imaginary parts can take positive and negative values. Magnitude is by definition only positive, right? So the only place where you can use dB is in magnitude. These are again angles. So again, dB has no meaning there, right? An angle, it's called the unwrapped, which is, it will not restrict the phase between plus minus 180 degrees. So that you can see the things more clearly. But again, for most cases, this is irrelevant for us. So if you want to look in magnitude, you can look at it in linear magnitude, or you can look at it in power, right? Sorry, in dB units. So the other thing you have to remember is the S11, the reflection coefficient, is by definition, what is called the voltage reflection coefficient. That's basically how it is defined, right? And phases are only relevant when you talk about the voltage, because that is a complex number. Power is not a complex number, but the mod square of this quantity gives you power. And in many cases, power is the most relevant quantity, because that's what you're worrying about. Don't worry about phase. That's important to remember, because when you say magnitude, this is magnitude of gamma. Which is the voltage magnitude. And we can check these things shortly. And when you put magnitude dB, this is actually the power in dB. So this is again a subtle thing, way defined for you to keep in mind. But majority of you in this thing, you had done this. Okay, and we'll see what happens when you do that. So we can look at this in magnitude dB, because that's the term we have been, like the units we have been familiar with. So let's set that up. So that measurement is set up here. And now finally, we have to define the frequencies, right? And here also, I saw that, the frequency ranges chosen were sometimes quite random. They had no relevance to the problem. So the problem already tells you what is the relevant frequency you're interested in. This is around 6 gigahertz, because you remember impedance transformer only does perfect matching at one particular frequency. And then it gets worse, and that's what of sort defines how much, what range of frequencies one can reasonably use this as a good impedance transformer. And that's related to one of the options in the question. So we are working around 6. So, let's go a little bit on either side, maybe 4 and 8, and set some reasonable step size. Doesn't have to be very small, doesn't have to be very big. This is sort of for 10 megahertz spacing. This really would depend on the particular problem, where if you're trying to find some very small feature in frequency, you might have to go find it. But for this, right now, we don't expect to see any feature, because only the source is connected to the load. Okay, so let me open the graph, and then we run this, and you see that as expected, there is no frequency dependence, and it's giving some odd value of minus 7.35 dB. Okay, that's just what the gamma is for a 20 ohm and a 50 ohm load. So, but let's just confirm where this number comes from. So I'll remove the dB just to see what's going on in this case, right? So this is saying 0.428. All right, let me open up a calculator here. So we know the Z and Z naught are 50 and 20. So 50 minus 20 is 30, and 30 divided by 50 plus 20 is 70. So 30 divided by 70 is 0.428. Right? That's exactly what it is here. So remember, I just told you that when you plot it without the dB, it plots the voltage reflection coefficient magnitude. And Z minus Z naught over Z plus Z naught is the formula for the voltage reflection coefficient. And here there is no phase, because everything is real. The phase is 0, basically. We can even confirm that in a second, but that's what is plotted here. But when we went to log units, so I have to now take square of this. That becomes power reflection coefficient. And then I have to take the log. Where is log here? Okay, so let's do that again. So 50 minus 30 is 20, 20 divided by 70. Then we do square, and I do log of that. That's minus 10. Okay, there's something wrong here. What is it? Oh, so I did 50 minus 20, I took 20, it's not 20, so it's 30. So it's 30 divided by 70, which was 0.428. And I do squared, 0.18. I do log 0.7 and then multiply by 10. Right? That's the definition of the thing. It's minus 7.35, right? Which is what we got here. If I go back to dB. Okay. So this, you have to remember that magnitude without dB is the voltage reflection coefficient, but magnitude with dB is the power reflection coefficient in dB. I don't know why they have chosen this, but it's because in dBs, we almost always only look at the power reflection coefficient. That's why it is like this. Okay. So, and the convention there is, the definition is 10 log ratio of powers, because gamma is basically giving you ratio of voltages. If you square that, you get basically ratio of power. Okay, so these numbers hopefully now make sense. Are there any questions here? Yeah, thanks, Panya, for the message. I mean, this is pretty standard stuff, so hopefully you guys have followed this. Okay, so we will stick to the dB units now, and now reinsert the transformer. So right now, this transformer is set at 50 ohms. So when you have a 50 ohm transmission line connected to a 50 ohm port, then in some sense, this transmission line really doesn't do anything, because there is no reflection happening between this port and this port. So it's almost like it's equivalent to having the port directly on this side, except there is a phase accumulation. But if I now look at this, I won't see any difference. The result is the same as the case where there was no transmission line. But if I look at the phase, which has no real meaning here, it is, oops, I made the mistake. Okay. So this basically just tells me that, okay, the phase is running with frequency, which is what you expect for a section of transmission line. It's not so relevant for an impedance transformer so much. And especially in this case, there's really nothing much happening. I'm just connected a 50 ohm port with a 50 ohm transmission line and connected to a load of 20 ohms. Having no transmission line, I can simulate that by just putting a 0 electrical delay here. And this is the previous case. And now there's just this overall phase shift of 180 degrees. Why 180? Because 20 minus 50 is really the formula, right? Z minus Z naught. So that you get a negative sign. So whenever you have the load being less than the source, you get a reflection coefficient with a minus sign. So the wave reflects with a negative sign. That's why you have this minus 180 degree phase. But of course, in the magnitude dB, there is nothing, it's the same as before. So now one designs the transformer. We know from the formula that the transformer impedance is basically square root of the load and the source impedance is what we need. So I can just write an equation there to do that, and then print it by putting this colon over there, right? So that gives you 31.62, and I can just put that value here. And this should be your impedance transformer. Oh, sorry, no, put the 90 back. Okay. So this is what you expect to see. Now we are looking at it in dB units. And again, this can be misleading, and you have to be careful when you put these plots to choose the axis correctly. Don't just go by whatever is coming on the screen. Now, what is supposed to happen when it is perfectly matched, and it's supposed to match at 6 gigahertz? The reflection coefficient is supposed to go to 0, right? So that means in dB units, it will go to minus infinity, because log of 0 is that. So maybe it's better to look at it in magnitude. And now you see that the reflection coefficient goes to 0 at 6 gigahertz, which is what we wanted to do. So the impedance transformer is doing its job, and then it varies because you're looking at mod S11. And this is, again, remember, this is linear reflection coefficient. So one of the questions here was, set up appropriate graphs to demonstrate the response and see the frequency range over which reflected power is less than 1%, right? So what does that mean? you have to choose the axis of the plots in such a way so that one can see this thing very carefully, right? So this, of course, is not the right plot because we wanted to look at power. Now, one could have used a further equation to calculate the power, which is just the square of this. One can do that. Maybe I'll show you. Actually, why don't I show you how to do that first? We had done this earlier by using this thing called output equations. So here I can actually add an equation corresponding to a measurement. So I have some variable which corresponds to a measurement. It's actually an array of values. So you can then manipulate that. So I can define port parameter S11 magnitude, and then I can specify this. So this is gamma mag, right? And I'll put V there to remind us that this is voltage. And then I can define underneath that gamma mag P. Okay. And I can define this as gamma mag B squared. Okay. This is now also available as a measurement here. So I can choose now, instead of the data source name being this, I have to go here and choose output equation. So instead of going to the linear thing, and then it gives me the name of this is sort of the equivalent of the schematic, but since we called it output equations, that's what it is. And then the equation name is gamma mag P, or these are the two things which are available. So we can now plot gamma mag P. It still by default expects that everything is a complex number, but here the way we have defined this is a real number, right? So you can either choose magnitude or real part, they will both be the same thing. If I now look at the graph, now instead of that linearly changing line, because that's what you'll get from mod of z minus z naught over z plus z naught, here you get this parabolic kind of thing, right? So this is one way of doing it, because now you can read the percent power. So we said, what was the question here? It said appropriate that demonstrate response, see frequency range over which reflected power is less than 1%. We can read off 1% here, right? Because it's 0.01 in reflected power is 1%. So it's basically this range here. So I could add a marker here, right? So close to this 0.01 value. And then I can now add a similar marker here. Okay. So this is the range within which the reflected coefficient is there. That's basically the range between these two markers. So after 5.18 gigahertz and less than 6.82 gigahertz, you have the reflection power to be less than 1%. So this is again like a standard thing we had discussed, that we usually consider 1% reflected power as sort of considered a small reflection. So anything which is better than that, it's good. And beyond that, it's not so good. So we can say that the impedance transformer works over this particular range. The same thing, if I now look in dB and I go back to my standard port parameter, S11 mag dB, right? So because of this minus infinity, the thing auto scales terribly. So we just have to fix this by adjusting the axis. All right. So let's go to the left axis, remove auto limits. And we know 1% is in dB is minus 20 dB. So let's maybe go up to minus 40 dB here. Right. So of course this will go down below, but you see those points are exactly the same where they were, because 0.01 is minus 20 dB. So it's like minus 19.96 and 19.95. So either of these two graphs would have been fine. This is all you had to show, that, okay, here is the range over which the reflection coefficient is smaller than 1. Okay. Any questions at this stage? Okay, I'll move on. So the next part of the question was, now design a two-stage transformer to increase this bandwidth. The goal is to maximize the frequency range of matching as in B, right? Which means what the frequency range as defined in B, which is the range of frequencies where the reflection coefficient is less than 1% or less than minus 20 dB in log units. An important choice is the intermediate impedance between 50 and 20 ohms. So this already tells you what the setup has to be, even though, again, this is something we did in class. You have to transform from 50 to 20 in two different steps. So you first have to transform from 50 to some value, and then from that value to some other value, right? So why is that? Because we know, or in fact, why would that actually help? Because we know that it is this difference, or this, so I shouldn't use the word difference because I don't mean subtraction, but it's basically, it depends on how different these impedances are, which you're trying to match. So here it's 50 to 20 ohms, and you got something like 5.18 to 6.82. Let me just freeze this graph here for reference. And if I now change this 20 ohms to 30 ohms, this should automatically compute the correct impedance transformer value, right? So now it's, oh, I should put this, sorry, 30. So now it is a different impedance transformer. But if you now look at this graph, you see that the range over which the reflection coefficient is less than minus 20 dB has increased now. It is now all the way from here, which is 4.46 to 7.54. So the smaller the difference between the impedances you're trying to match, a single section impedance transformer gives you a larger range over which the matching would work better. Right? And it's kind of intuitive, because if the two are same, then it's matched everywhere. But as they get further and further away, then you have less and less matching. So we can now look at one on the other side. So instead of 20, if I put now 15 ohms here and here, now you see that this curve is narrower than what we had before. So the range over which the reflection coefficient is less than minus 20 dB has become smaller. So it is this intuition which tells you that if we now transform in 2 steps or more than 2 steps as well, then you can potentially get larger bandwidth, right? That's the idea behind a multi-section impedance transformer. So that is the thing one has to do here. We go back, set this up. In fact, let's now define a quantity called ZL for our load. And that way I don't have to keep changing this. So now I need 2 sections. Okay, so I'm just going to copy this and put it here. Now the question is, what is the sort of optimal way of approaching this problem? And the problem gives you the hint, right? It says an important choice is the intermediate impedance between 50 and 20 ohms, right? Because we are doing it in 2 stages. Instead of going from 50 to 20 directly, we want to go from 50 to something else, and then from that something else to 20. So there's really this one unknown quantity which we want to figure out. right? So because in this circuit, now you have ZT, in which I should really change now, because these two impedance transformers characteristic impedance will not be the same because they're transforming different pairs of impedance. So I need to define ZT1 and ZT2 for the two variables here. ZT1 as before is for the first one, but now the question is, what should be how should we define that value? And this is the intermediate value, right? So I define another variable, and that's the only variable which should matter, which should be able to tune, and everything else will be in terms of that, right? So let me call this Z, I don't know, mid or something, right? And I'll put some random value here. So we are going from 50 to 20. So I don't know, let's say put 30 here or something. I'm sorry, this should be now ZL to be correct. So what this Z mid is going to do, it's the impedance sort of some imaginary value here in the middle, right? That's what this is telling, but there is no component whose value is Z mid. So what does this do? This immediately determines what the two transformers should be, because the job of the first transformer is to convert 50 ohm to Z mid, and then the job of the second transformer is to convert Z mid to ZL. ZL is 20 ohms as given the problem. So that's what I meant by, choose this one thing. So this is the only thing I should be able to tune, and this is what you're going to find by tuning this value. We will see when the impedance is maximized, because there has to be an optimal choice here, right? You cannot say, okay, I'll go from 50 to 49 and then 49 to 20, or 50 to 21 and then 21 to 20. That obviously probably wouldn't work. And that's what we want to see here. Like the problem has to be set up in such a way that you're able to see this. So this is the only thing we have to define. Then everything becomes trivial, because now you just say, okay, ZT1 is transforming 50 ohms to Z mid. So ZT1, I know what the formula should be. It's 50 into Z mid, right? And then I have to set up, should be ZT1. Put it down here. And ZT2 is transforming Z mid to ZL. So it's just square root of Z mid into ZL. That's it. That's all that had to be done, right? And now you just have to tune this. So it gives you the, what happened here? So, okay. So just make sure these numbers make sense. ZT1, which is matching 50 ohms to 30 ohms, is giving you something like 38 ohms for this first section. So it's somewhere in the middle of those two, which is what it should be. And then ZT2 is transforming Z mid, which is 30 and 20. So it's somewhere in between that. Okay. So that's why I realized that, because it was giving 100 ohms, I realized I made a mistake, right? So this is what, but right now I've chosen Z mid arbitrarily. Now I put a tuner on that. And as I change this, all of these should change. So this is all we had to do. Okay. Now let's run this. Remember the previous curve here is for the single section transformer, which went from this 5.18 to 6.82. Now we have a response which is already quite broad. So we see that it's working, but now we want to find the optimum. So this Z mid is right now set to tune between 50 and 60, I guess. That's okay. So let's see what happens. Set up at 30 now. If I reduce this, you see that it's coming closer. So that's not the right direction. I increase this and it gets wider. And then at some point, it comes back again. Right? So this is exactly what one had to see, that there is going to be an optimal value for Z mid where the response would be the widest, which is what we are trying to do. We are trying to make this as broadband as possible. So somewhere around here, it turns around at around 31.6 or so. But of course, I can do a finer job. Let me set this up. Now it's coming back in here and there. So somewhere around there. This is 31.6. Okay. And now the bandwidth is all the way here, right? So this is the minus 20 dB point. So it has increased from this point. This point has gone all the way over here. Like this was at 5.18, and now it is at 4.18. And this point has gone similarly on the other side. Right? So this matches over a much broader range. And we have found the optimal value by just empirically. I have not used any formula here. That's what the problem said. Set up the relevant quantities in the tuner and use equations to calculate the required parameters. What does that mean? Set up the relevant quantities means define Z mid, which is already mentioned here. An important choice is the intermediate impedance between 50 and 20 ohms. The relevant quantities is that, and then you define that equations. Using equation, you define the impedance transformers for the two sections. And then you should be able to tune one relevant parameter, which is Z mid, while the others get calculated automatically. I mean, explicitly, everything is written here, like what one had to do. And again, like even for this problem, very few of you actually got this, right? Find the optimal point. And then it says, okay, you know, this is sort of testing your understanding. Can you motivate the value for the intermediate impedance obtained in C? So we got this value of 30.6. So, you know, can we say something about this value? So let me maybe ask you, like, how is this 31.6 coming from? Is it connected to something? Can we make a guess here? I mean, clearly it has to be related to this 50 and 20 ohms somehow, right? So if I try this,
it's basically square root of Z and ZL, like.
Yeah, so let's see this. So let's call this Z mid calculated equal to square root of 50 into ZL. So that's exactly what it is. We haven't really derived this, but you can go through this equation setup and figure out what will give you the maximum bandwidth. But this is what I meant. And the thing is, if you had done the first part of the problem correctly, you would have seen this number before, right? 31.6, because that is the impedance transformers value you got for ZT, because this is the same formula for a single section impedance transformer, right? So then it goes on to say, if we now split each transformer into two further stages using the above argument, what response do you get, right? So the point here was that I don't need to recalculate or do this business of tuning, because now if I have multiple sections, then I'll have to tune too many things at the same time, and manually we will not be able to find the optimum. But the point it's making here is that you have now two transformers, so we can now consider this as two separate problems. The first transformer is transforming 50 ohms to Z mid. So I can now consider this as a separate problem and say, well, how do I now split it into two? Right? And I can split it into two in exactly the same way where how I split the whole thing into two, which means that I will have to choose a mid point here, which is going to be square root of 50 into the previous z mid, right? So 50 into 31.6 square root would be the new z mid, and using that new z mid for the first section, I can compute what the transformers, how this transformer gets split into two. And then the same thing you do for here. This is now transforming Z mid to 20 ohms ZL. You split it into two by using a mid frequency, mid value here, which is just the square root of 31.6 into ZL. Right? So that would split each individual parts using the same logic how we split this. And that will give you a larger bandwidth. So that's what one was supposed to show in this problem. So, this is what I meant by saying that all of these things we have actually done in class, the single stage, the double stage, and there's just, a slight twist for you to approach the problem correctly, which actually has nothing to do with microwave engineering or anything. It's just basic logic, right? So, which is why I was very surprised. Now, what happened because of that very silly mistake, which many of you did with the setting up of the measurement itself, which is where everything sort of went haywire. Let me, actually, I guess I can show it here as well. So this is how the graph should have looked like. But if I plot the real part in dB units, okay, I guess I should, I'll just get rid of one of the transformers here. And I'm going to define the Z mid as the same as ZL. So that will go back to the case of the single transformer. Let me do the right thing here. No, made a mistake. So T1 is 31.62. That should have worked. Why did it not? Yeah, okay. Maybe they didn't like the short circuit. Right, so this is what we had before. Now, if I do real part, yes, I need to auto scale this now. Or maybe at least go to minus 100%. Okay, this is weird. It's behaving differently than what I had seen in some of your plots, but maybe because there was something else wrong as well. What is the value? Okay. So this is what the real part just looks like if you just look at the reflection coefficient. It goes to 0 and then it's all negative. So the log is just some weird thing it will give you. What happens? Imaginary part. Maybe it's doing some weird correction here. of course, these numbers now no longer have any meaning because the magnitude of the reflection coefficient cannot be the dB of the real part. But for some reason in this schematic, this plot is looking different. Maybe the parameters chosen for the impedance transformers are also not exactly correct. What happens if I change this to some other value? Let us say 30 ohms. 5 ohms. Yeah, I think this is what I remember now. Yes. So, it gives this double peak because it's not matched. But when it is actually matched, it still gives only a single peak. So I saw these two peaked structures, not maybe so far off, but close to each other. And that should have hinted you that this is not showing the standard behavior, because you should have at least known or remembered that a single section impedance transformer has only one dip and that too at the correct frequency at 6 gigahertz, right? And here the peak is at the wrong frequency. Let me bring this value closer to the expected matching point, and then you get this. So like it's matched at the wrong frequency, that itself should have given a hint that something is wrong. But if you look at this in MACDB, you'll always only get one peak, one dip. So when you are not matched, it's just the dip doesn't go all the way to zero. It just goes up and down, and the shape will change. But you won't get this double dip. Then the double dip is happening because if you look at the real part crosses zero at two different points. Whereas exactly at the matching point, it crosses zero only at one frequency. And because there are two zero crossings, when you're doing negative numbers of log, I mean, of course, this must be using some convention of maybe it converts it into a positive number and basically computes the mod of the quantity and then takes log. You get a dip because it looks like it's matched here and it matched here. So that, of course, has no meaning here, because just looking at the real part is not enough. If you're looking at in this particular page, you have to look at what the imaginary part as well. The imaginary part is not zero at those crossing points. So that means reflection coefficient is not zero. So only by looking at the magnitude can you tell, because it takes both the real and imaginary part, and the magnitude never goes to zero anywhere. So I think this basically threw people off completely, but again, this was sort of nonsensical because this is not what you measure. So please be careful about this going forward. So I saw this double peaked curves for several of the exams. Okay, so that's basically for the first question. So this is all what you are expected to show. Are there any questions now at this stage? I mean, again, nobody's asking any questions, so I really don't know whether you have followed this or not. No questions? You can raise your hands if you have a question. Okay. We'll move on to the next question then. Okay. So now this one maybe was slightly less familiar because we didn't spend that much time on the resonators. At all, like when compared to the impedance transform, because we kept going back to it over and over again. But again, the problem, the way it's written down, it's very descriptive and it gives everything you have to do. Then it was just about setting up the measurements correctly and trying to think about it a little more. And at least some of the things which we had mentioned about, loading of a resonator with a capacitor and things like that. So I'm just going to pause here for 2 minutes and get some water to drink, and then we'll resume this. Okay, let's continue. Okay, so this question had one complicated part, which is the last one. But apart from that, it should have been at least straightforward to set up. I mean, there are some things which required some additional thinking based on some of the things we had discussed in class. So this is this thing about the current measurement. It says existing schematic graph is an example to show how to measure currents. Okay, see part E, the earlier parts don't depend on that example, and I have kept the graph disabled. Okay, that was just because the nonlinear simulations which are needed for measuring current are slightly more time consuming. I mean, but for a very simple thing, it would have not made much of a difference. So that's what is shown here. I'll come to that at the end. Okay. So question says, set up a transmission line resonator in the following two ways. Two different schematics. Okay, so you have to make two different schematics. Use a lambda by 2 section. So that means 180 degrees of 50 ohm transmission line at 6 gigahertz. Everything is given with one end open and the other end connected to a 50 ohm port. So I just don't ask you to make a transmission line resonator. I told you exactly what needs to be drawn. 50 ohm port via a coupling capacitor of 5 femtofarads. Use a lambda by 2 section of 50 ohm transmission line at 6 gigahertz with both ends connected to 50 ohm ports via a coupling capacitor of value 5. So gives exactly. So it also clarifies that. So circuit in 1 is a 1-port network because there's only 1 port, while the circuit in 2 is a 2-port network. Okay. So this is, can't be simpler or explicit than this. So we now say, let's call this T line res 1-port. Transmission lines. So 6 gigahertz, remember lambda by 2, so it's 180 degrees. And then I had to put a capacitor on one side. And it says 0.05 or 5 femtofarads, which is 0.005 picofarads. Right? It's 5 femtofarads. Yeah. You put one port. And it asks you to leave the other port open, right? Now, does it say here what type of resonator? No, it doesn't. So what type of a resonator it is in terms of the boundary conditions, right? So one end here is open. So this will have a voltage antinode or a current node. The other end is a small coupling capacitor. So even this is a voltage antinode, maybe not as big as that one. So this is what is called as a half wave resonator or lambda by 2 resonator. The wave profile would have looked something like this. So this is a half wave. So this is my middle line. So there's a voltage antinode on this end and there's a voltage antinode on this end. But that's also the part which is coupling to the port where you can do the measurements, right? If you keep both ends open, then nothing is connected, then you can't measure anything. So this is how you can couple to it. You can compare this to a Fabry-Perot resonator, like an optical resonator. You have one mirror here, and then you have a partially transmitting mirror on the other side, right? So waves can, back and forth, but here they will leak out as well. And they are also, energy is also coming in from this side. That's what this type of a resonator is, right? We had mostly in the early part of the class looked at LC resonators, but this also we discussed towards the end. We had shown some examples of that. But anyway, this only, it gives you exactly what to draw. So this is what one had to draw. Okay. And the second schematic, I can just copy this. And so T-lin res 2 port. And here I just had to make the same thing, but now the other side is also has identical capacitor and a 50 ohm port. Right? So because earlier also I said that this very small capacitance is like a weakly transmitting mirror. This is now 2 mirrors, both of which are weakly transmitting, right? So you can have energy leaking out of both directions, but still these are both voltage antinodes on either side or current nodes. So it's a half wave resonator. So the first thing part of the question is set up reflection coefficient measurements to check the resonance and reflection for both schematics using port 1. So it also says that you set up just a reflection coefficient measurement on port 1. Right. So here also I found that, and this was one aspect which I think I had gone over and over again in the class, was that when you do a reflection measurement on a resonator and there is no element which can dissipate energy, right? So remember, this here is a section of transmission line which is a perfect transmission line. There is no energy for it to dissipate anywhere. So in order to look at the resonance, you have to look at the right quantity, right? And also set up the right frequency range. And again, the hint is there. It's a λ/2 resonator. It's at 6 gigahertz. So the frequency range, has to be around 6 gigahertz or so. And you're not going to see anything in magnitude. So let's draw the graph now. Okay, so I'll choose the one port first. There's only one port. And if I look at magnitude, and let's say I look at it in dB, sorry, frequency has to be set up. So again, I'll choose 4 to 8. And, if you see something like this, just no need to panic, right? Look at the axis. It's saying 0, 10 minus 15 and minus 10 minus 15 here. There's no meaning. It's basically just 0 everywhere. 0 dB reflection means what? It means a reflection coefficient of 1. So let me get rid of the dB, and now you see that it's just reflection coefficient 1. You won't see any resonance on the magnitude. We discussed this in class so many times when we looked at LC resonator. You have to look at the phase or the real part or the imaginary part, right? So let's go to the real part. Okay. So now you're seeing something sharp here. All right. I can imagine that at the beginning of setting up this problem, you might not have had a sense for, how sharp this resonance is going to be, and you could have chosen a frequency range which is maybe completely off. But here you see something. So what should be the natural instinct there? It's like, okay, it looks like all the action is right in the middle. I don't need to sweep such a big frequency. So you go and you change the frequency range so that you can see what is happening. I think in some cases, you saw that there was nothing and that was it. That was the end of the problem. So let's go to somewhere closer. I mean, this looks fairly close to 6 gigahertz. So let's try 5.8 to 6.2, and then increase the resolution so that there is sufficient number of points. You can see the, right. Look, it's still really sharp, but now you see that you can see it a lot more clearly. It's going from +1 and it's going almost to -1. And this again, you should have remembered that in resonance, real part goes from +1 to -1. So it's still not, the frequency range is still not good enough. I have to go even further. Right. So, maybe you could have zoomed in here using this thing and gotten a sense for where the curve is. And okay, that's not the right one. But let's say if I put my cursor somewhere here, I can read off the values. So it's like 5.975, right? So it's a very sharp resonance, and this has got to do with the value of the capacitor that was given. I saw in some cases the value of the capacitance was left to the default value, which comes, when you place the capacitance from the circuit, and that would have given a completely different. That's usually about a picofarad or something, depending on what settings you have on your thing. But I don't even understand how that, you can do that, because the problem says use a 5 femtofarad capacitor. Okay. Now it's better. It could still be thing. And remember, I was centering all of my frequencies around 6, but clearly the resonance is not at 6 gigahertz. It's slightly below. It's around 5.982. Right? So we probably should go from 5.975 to maybe 5.98, maybe 999. Now we can zoom in a little bit more. Right. So finally, we are seeing the resonance properly. So looking at the real part, it's going from 1 to -1. This might be, if you remember, some of you remember the measurements from just the LC oscillator, the parallel LC oscillator, it goes from -1 to +1. It's inverted. This inversion happens because of this coupling capacitor. That gives you a 180-degree phase shift, so it flips the whole thing, but that's not really a problem. You can also see that in the phase. If I now look at the phase here, you see that it's not the thing we are used to seeing, which typically looks like looks like this, right? If you remember from your classroom that the resonance in phase looks like this, and the zero, where the zero is, that's the resonant frequency. So here this is starting at 0 instead of starting at 180 degrees because of this 180-degree phase shift. I could have chosen the unwrap option here, and then it would go from 0 to -360, and then the curve is in the same way, goes in the same direction, right? But it's a lot more convenient to just use the real part because it has this nice dip or peak in this thing. So this is what you had to do in the first step, and part of this is just exploring that, does your graph make sense? What is the correct frequency range? You've been told it's a resonator, so it's going to have some frequency response. And I think many of you didn't even get to this point, because maybe you were just looking at it magnitude, saw nothing, and basically that was the end of it. Okay, so that's now the reflection coefficient of the resonator in schematic 1, which is the 1-port resonator, right? So now we can just add the plot for the 2-port one and the same one. So let's use this duplicate measurement thing, change the data source to the tail in 2-port and still use the same port 1, 1 and the real part. Okay, now here is a problem. You don't see anything in this real part, right? This is the pink line here. It looks flat. It seems to indicate that what does this indicate? Sulagna? Sulagna, can you hear me? Your voice is not coming through. Hello?
Maybe resonance is somewhere else. That's why we are getting flat line.
Sorry, Argya, yeah, tell me.
Maybe resonance is someone else. So that's why I'm getting the same straight line in this frequency range.
Exactly, right? So it's not there in this frequency range. Remember, you are looking at a very narrow range. So the resonance must be somewhere else. Okay. So what then you have to do is you have to now expand the graph again. Probably better to create a new graph first. So let's maybe just duplicate this graph and get rid of the measurement on the 1-port here, right? And now you have some hint that, okay, it's going down on this side. So this means the frequency is probably to the left, right? So let's expand the range. Let's go to like 5.8. We'll have to reduce the resolution a little bit, otherwise that will be too many points. But we'll again like find the rough point and then zoom in. Okay, so there is the, so this is at 5.964 gigahertz. So maybe we go from 5.95 to 5.97. Okay. So it's, you see the dip, but do you notice something different? Argya?
Yeah, it is 0 to 1, not -1 to 1.
Exactly, right. So what does the question ask here? It says, explain the differences you see in the two plots. Okay, so let's now set it up in such a way that we can see both of these curves in the same. So we need to go from 5.95 to 5.998.
5.982.
This curve, right? So I should go to, oops. So now you have both of them on the same graph. So as Argya pointed out, the blue one, which is the single port one, goes from 1 to -1 and then back to 1, whereas this one goes from 1 to 0 and back to 1. So why is this difference? I mean, clearly we've made this circuit is slightly different. There is now a second port here. Remember what we talked about just in the beginning, that when I had a single port and there was nowhere for the energy to go except come back, you will not see any response in the magnitude because all the energy is coming back in steady state. So the magnitude doesn't change, and information is there only in the real part, imaginary part of the phase. Now, that's really not true in this case, right? Because now there is this other port. Port is a place where energy can go. Remember, I said that's like two mirrors now, the energy can leak out. So instead of now real part, if I actually look at the just the magnitude for both these curves now, one of them you've already seen, but and as expected, the previous one is just flat, but this one, the two-port one, actually shows perfect absorption at the resonant frequency, right? Just the pink one is the two-port one, and now we are looking at magnitude of reflection coefficient. And the reflection coefficient is going to 0 exactly at the same point we saw the real part reaching 0 from 1, right? Which is the same as the resonant frequency. Why is this happening? This is happening because now that power is actually coming out of this guy. Okay, so we can verify that by looking at S21. Remember, we are looking at S11. I can now change this into S21. Actually, let me freeze this so that we can compare it. And I'm going to change this guy to S21. We still plot magnitude of dB, and you see this the magnitude now going from 0 up to 1 at the frequency. In fact, I should probably plot S11 and S21 at the same time. Here, I've now shifted both measurements to the two-port system. So I'm now, blue is the reflection coefficient from one of the ports, and you saw what it is. It goes from +1, no reflection, to perfect absorption. Sorry, all reflection to no reflection, which is perfect absorption here. But absorption here means what? The transmission line still cannot dissipate any energy, right? It can. So it's now, because we have second port, we looked at there and we see that at that same frequency, the transmission magnitude is 1. So that's where all the energy is going. In this circuit, on resonance, all the signal goes through the system. And that's why, from the perspective of one of the ports, it looks like it's perfectly absorbing the power, because that's going. And that only happens exactly at one frequency, right? It's then, this recovers back to 1, and this transmission goes back to 0. For the single port case, of course, there is no such option because there is only one port there. Right? So these were the observations you're supposed to make in this first part of the question, after, of course, drawing and setting up the resonance. Just to complete this, the circuit for the two-port case is perfectly symmetric, right? There is no difference between port 1 and port 2. So you would, if I now change the S11 into S22, it looks exactly the same because there is no difference between the two sides. And indeed, if you put power from the other side and look at the reflection coefficient, it will look like this. And similarly, I can measure S12, which is the transmission in the opposite direction. And that also looks exactly the same. So now this is, of course, a linear reciprocal circuit. So S21 and S12 being the same is as expected. But S11 and S22 need not be the same in general. But in this case, because the circuit is perfectly symmetric, I cannot tell from looking at the diagram what is port 1 and port 2, like there's no difference. So their response should be identical in the two cases. Okay. So I hope this part is clear why the absorption is present in one case because of the presence of second port. And the real part, what we saw earlier, let me go back to the real part of the reflection coefficient for the two-port case. The fact that the real part only goes from, let's look at, right? So again, the colors got interchanged, but the pink one is the one port reflection coefficient, which goes from 1 to -1, and the blue one is the reflection coefficient. It's on port 2, but port 2, port 1 is the same. It goes from 1 to 0. This is purely just a consequence of having this loss there, okay? This is what happens when you have a dissipation, apparent dissipation in the resonator when measured from one port. So here the dissipation is not happening in the resonator, but it's because there is a path for the energy to go out of there. So from perspective of one of the ports, it looks like there is loss. So the fact that the real part goes from 1 to 0 is actually a way how you know that, okay, there is some dissipation. Of course, that also reflects in the fact that the magnitude now shows a dip as well. There is similarly a change in the imaginary part as well. If I now plot the imaginary part of both of these reflection coefficients, you see again there is this difference. So for the single port resonator, it goes from wait, did I plot them? Yeah, okay. This again is because of the negative sign, it's a little bit confusing, but you see this goes from 0. Oh, no, sorry, it's fine. It's just the signs are inverted. So it starts from 0, then goes to -1, then flips to +1, and then comes back to 0. Whereas this one only goes halfway, like -0.5 and then +0.5. And this is entirely because of the presence of the second port through which it's leaking. Okay, so let me change this back to port 1 so that we are don't confuse things here, right? And go back to this thing. And now I'm going to, so the next part of the question was explain the differences you see in the plots. Okay, those were just the observations you had to make. Then is the resonant frequency and total Q different for the two cases? Okay, so the first answer we already seen, the resonant frequency is different. The total Q, if you remember, it's related to the width of these curves, right? And it's probably easier to see it in the real part. So let's go back to the real part for just a minute. So the thing I want you to note is that not only is the frequency shifted, this thing is a little bit wider than this one, right? So the way to look at it, if you remember from our discussions, is that you look at this full width half max for the Q factor, right? The bandwidth. So half of from 0 to 1 is 0.5. So it's this and this point. And here, because it's going from 1 to -1, the midpoint is this point here at 0. So you have to look at the difference between these two guys. So clearly this distance here is narrower than this one. What does that tell you? That the single port resonator has a narrower bandwidth, which means higher Q, whereas the two port resonator has a broader bandwidth. Right? So the answer here is yes, both resonant frequency and Q are different for the two cases. And then the question is if yes, can you adjust? What can you adjust in circuit 1 to make the resonant frequency and total Q match for both circuits? Right? So I wanted you to look at some change in the circuit 1 in order to make the two look similar, right? Even though they're constructed differently, what can I change in that? Now I'm going to do this in a inverted way by looking at this plot and changing something in circuit 2. Now, by this point, it should be obvious that whatever differences are coming is coming from the second port, right? So the fact that there is now an absorption, like a dip in the magnitude as you measured from reflection, that is because of the presence of the port here, okay? But the fact that the frequency is different is a bit strange because the length of this resonator is still the same. But this is related to the fact that now there are two capacitors connecting on either side, right? If I put a tuner on this guy and look at the plots, right? So right now I have put a tuner on the second port or the capacitance of the second port, which is corresponding to this. So let's freeze these traces for reference and then tune that capacitance. So remember, not having a capacitance in this picture is equivalent to the capacitance value going to 0. So it means I need to reduce the capacitance. So let's see what happens as I reduce the capacitance here. So I'm reducing the capacitance of this guy, right? This guy here. So sort of I'm decoupling it from the second port. So you already see that this frequency is now shifting upwards, but at the same time, the real part is also going past 0, right? And you see it's also getting sharper compared to where it was before. Let me set this to 0. So when I put it to 0, it exactly matches this one. I mean, that's obvious, right? Because if I now put this to 0, it's as if this part of the circuit didn't exist as well. And it also means that even though this port is present, this port is not playing any role because it's actually, for all practical purposes, this capacitor is disconnected at this point of time. That's what 0 picofarads capacitor. Remember, the impedance of a capacitor goes as 1 over omega C. So if C goes to 0, that impedance is infinite. So there's no connection between these two points here. So by reducing this capacitance, you make this match as the single port case. But what I was asking was the opposite. And let me set this back to 5 femtofarads. Okay. What I was asking is, what can I change here to make it the same as the other guy, right? At least in terms of the frequency and the what can you adjust in circuit 1 to make the resonant frequency and total Q match for both the circuits? So I was careful here. I didn't say make the reflection coefficient match, right? Because what we just did was make the two circuits effectively identical by setting the capacitance to 0. That's not the same as in this problem, because I'm only asking you to change something in circuit 1 to make the frequency and the resonance match. Because if I'm not changing anything here, that means this extra dissipation which appears from when you measure from one side is still going to be present, right? So what you had to do, like when you realize that it's the capacitor which is causing the problem, and because there are two capacitances here, it shifts the frequency more than the frequency at the 6 gigahertz. So if you remember, we had discussed this, I think, in the context of LC circuits with coupling capacitors, but also in the context of the resonators as well, but maybe we didn't spend too much time. So this capacitance has a sort of a loading effect, that if you model your resonator as just a parallel LC circuit, this extra capacitance, which is the coupling capacitance and allows you to control the Q or the dissipation, also shifts the frequency because that capacitance adds to the total resonance. So now, because there are two of them, they will add together and shift the frequency more. That is why this frequency is further shifted from 6 gigahertz. So 6 gigahertz is the bare frequency, and there is some shift because of one capacitance, and now there is an additional shift because of the second capacitance in the case of the two-port resonator. So I want to now match the one-port resonator to be similar to the two-port resonator in terms of its frequency. So what I have to do is I have to do the opposite. I have to increase the capacitance on this guy. Right. So I'm going to put a tuner here, and let me get rid of this guy to prevent confusion. I go back here and I start to increase, because I need to bring this lower, I have to increase this frequency. But remember, this is still going to remain from +1 to -1 because it still is a one-port circuit. Okay, so this is how you can bring the frequency to this particular point. Now here it gets a little bit tricky, and if you had not gotten only this part, it would have been okay. But the frequency is matched, but is the bandwidth really the same? Because now, if I look at again at the midpoints, this is the width here, whereas the width for this guy is still smaller. Okay. And that's essentially related to the fact that the Q factor changes, I think, as the square of the capacitance, whereas the frequency changes linearly. So even though in order to shift this resonator frequency to the same as this resonator's frequency, because 5 femtofarad, 5 femtofarad, total capacitance is 10. So that's why it exactly matched at 10 femtofarads. But the Q factor, now the coupling of this 10 capacitors is actually higher than it goes as the square. Whereas in this case, because it's two independent ones, it just adds, the loss of this guy plus this guy just add together. So because of that, when you shift the frequency, the line widths don't match, which means the Q doesn't match. Okay. I mean, the problem looks much worse here because of the fact that the curve only goes from 1 to 0, so it artificially looks narrower. Whereas this one, if I had like stretched this out, it would have been a little broader. But what you have to compare is basically this point here, like halfway point between the extremas. So for the pink case, it is this one. So maybe actually let's put a marker there so that we can explicitly see how much it is. Okay, so here it's going from 9635 to 965. So it's about 1.5 megahertz or so. And here 963 to 964. Oh, it's actually, am I reading this incorrectly? Maybe they do match. It's clearly not the same frequency as that one. 96387, 9635. Okay, yeah, it's I mean it's a small difference, but yeah. Let's just make sure by zooming in a little bit more. Nine six two nine seven. So this is 9635 and this is 9638. Yeah, okay, this is clear. It's not the same. Okay. This changes in the last few decimal places. It's roughly half is sort of what we expect. Because one is like square and goes to like 4, and the other one is just adds like 2. It's about a factor of 2 difference between these two. Okay. So this is what we had to make an observation here and explain. So this is a slightly harder problem, and again the idea was that the first problem is very, very straightforward. Everything is same. Here again there are some basic things you have to set up, just make observations, and then there's a little bit of thinking involved based on what you've done in class. But again, I think because many of you are not able to even set up the problem, you couldn't do any of these things here. And the last part is, of course, completely different. In part D, it says set up reflection coefficient of circuit 2 from port 2 as well. Is it identical to that from port 1? So we already discussed that because it's a symmetric circuit. Okay. So this fifth part is, I mean, very tricky. I mean, I was not expecting any of you to get this, but sort of like a bonus question. This was related to this idea that when you have a 1-port versus a 2-port resonator, how does the system actually get excited? Like how much energy is there in the resonator? So the current is actually a proxy for measuring the energy, because the energy in the resonator, if you have inductor, the energy is like half Li square. So that was the idea here, because we are now in all of the other measurements, you're only looking at reflection coefficient. There's no question of power or anything, right? It's all a ratiometric measurement here. So again, it tells you everything. Schematic current measurement, the graph can show us an example of measuring currents in microwave office. A parallel LC oscillator as shown is driven with a source with impedance 50 ohms. Please note that the source type is different now and allows a power value to be set, because this is for the nonlinear simulation. The schematic also includes a current measurement device in the inductor arm to measure the current through it. The measurement in the graph shows how to set up a nonlinear current measurement. Right? So if we now go to this thing here, it's a standard LC circuit. The only difference is that this port is of a different type, and that actually comes from just double clicking it, and in this option here, default is always termination, which means there's no reference of any power. You change it to source here. Okay. So again, you're not supposed to understand these things in any detail. It was just given to you that this is what it is. And then you had a current meter here, which can measure the current through this branch. And the measurement here basically tells you how to set up. So all you had to look up here was that, okay, where is this measurement set up? It's in nonlinear, it is current, and it is something called I component. And you have to choose this measurement component here, the data source name correctly. And just have to set this up as whatever it is here. As a, you don't have to understand why these things are here. And then also it shows magnitude here, right? So that is the thing you have to do. You have to change the port to this type, and you have to add a current meter here. Now, how does one do that for both the cases? So I had asked you to put the current in the the meter in the current antinode. So remember that this is a system where we had voltage antinodes on both sides, which meant currents are 0 at the end. So you had to put it in the current antinode, which so remember I had drawn the wave like this for the voltage. The wave for the current is basically the opposite, right? So you have the current antinode is right in the middle. Okay. Now, how does, I mean, again, this was a trick question for you to think a little bit. How do I change this circuit to access the middle? Because I can't access the middle here, right? But it was very simple. All you had to do was to create two 90-degree sections, which is exactly the same. But now you have this point here. That's it. See, this circuit is exactly the same as before. If you go back to the graph here, you will see nothing has changed. Okay, it's now trying to do this simulation for the nonlinear part. Let me just disable that. this was again a slightly trick question, but it's not so complicated. So now what you do is you double click this. But I guess I didn't give this information of double clicking, but all you could have just gone here and copied this port into this guy, right? And I gave you the power, so it's already by default 0 dBm. And now again, you had to go to the schematic, copy this current meter and put it here. That's it. Now you have to set up the measurement. So I'll set up, I guess I'll use the same one, but change the schematic now. This is schematic, no, T-LIN-Res1 port. Measurement component is there, nonlinear. Sorry, the current icon. This shows anyway already selected. We have to set this harmonic index to 1. Magnitude. Enable this measurement. Let's look at this graph now. Oops. Run this. Hopefully it will run. That's it. You see, now it's plotting the current in the center of the resonator, which is the current antinode. And it again shows a peak, right? Which is what you'd expect. You will see that there'll be current will be maximum at the resonant frequency. And does it match? So this is showing something like 5.964. If I go to my other plots here, this is exactly the same frequency, 5.964 gigahertz, right? So that's why, the example was given. You just had to copy it into this case. And of course, you had to realize this trick that I should split the 180-degree sections into 290-degree sections and put this thing in the middle, right? You can see some interesting things here. I mean, this is sort of not part of the problem, but for example, I could choose where to put this current meter in the middle by defining a variable, right? So I could say like the first electrical length part of the on the left side, I can define that length. And then I can define the second one as 180 minus that one, right? So then what it means is that if EL1 is 90, they're both 90, that will be the middle. But if I now tune this, I can change this from one place to the other. And that sort of, you can see what happens in that case, right? So let's do this. Let's freeze this trace and open the tuner. And right now it's at 90. So let's say I make it 120, right? So I'm moving the current meter to sorry, let's check if I made a mistake. 90, 180 minus 90, that's correct. So this is 120, that would be 60. Oh, sorry, not 180, no, right? Yeah. Oh, sorry, I didn't change, my mistake. This had to be EL1, right? Sorry, yeah. So I change this to 120. And you see all that happened was the current dropped, right? The resonant frequency is in the same location. I make it 150. You're moved away from the current node towards, you're moving towards the current node now, the current drops. But of course, it will still be maximum at the resonant frequency. Same things happens on the other side. If I go below 90 degrees, so if I go to 70, it's again smaller. If I go to 50, it's again smaller, and so on and so forth. Right? So all the problem asked was to set this up for both. So all you had to do now, do the same thing here. You split this into two, put a current meter, put the port on one side, and then compare these current curves. And it also asks you to use the adjustment made in part C so that the response of 1 and 2 is identical. Okay, I guess maybe this one is slightly misleading because they are, as we saw, they are not identical. The frequencies are the same. And replace port 1 in both 1 and 2 with the type of source explained above. So it basically says that so this port has become the source port, and this port in this case should also have become the source port. And all it asks you was to compare this curve for both those cases. And then I said that I will ask questions about this in the oral, and that was basically to explain why they were going to be different. And one of the things we already discussed, of course, the Q factor is different. So if the Q is different, the currents in the for a fixed excitation, the amount of current in the system will be different. But also the fact that there's one port versus two port also creates a difference in that. So this was sort of an open-ended part of the question, but this is basically what you had to do in this particular problem. Okay, slightly more difficult than the first one, but still, if you had just read the things and not made very obvious mistakes. So what were the mistakes here? The first mistake was choosing the wrong measurement to find the resonance. The second was not realizing that one had to zoom in to the frequency of the resonance to find the signal properly. And that was it. And because of those things were not done, everything else didn't make any sense at all, because you couldn't do any of those, the next steps. So, because of very elementary mistakes which shouldn't have been made. I mean, if you had even paid a little bit of attention, which is why I was quite shocked that, and why I decided to, not just end the story there and give you another set of lectures to explain these things. But I mean, I don't know, you still are not asking me any questions, so I hope this is not a waste of time.
Sir, can you repeat about dividing the line? I didn't understand. What? Dividing the transmission, like putting it in between.
I mean, this is just very obvious, no? So I initially had, because I had asked you to make a 180, a lambda by 2 resonator, this is what the circuit is, right? Now, the current antinode is right in the middle of this transmission line. The transmission line is something which has a finite length, right? Now, in this particular circuit, how would I put anything in the middle? Because I don't have access to that point, right?
Yeah, I got it.
So all I had to do was because I can construct 180 degrees out of one section, or I can construct them with two sections of 90 degrees. They're identical, but now I have access to the middle point. I can break this up into any different ways, right? And by using this tunable parameter here, I also showed you that you can, in the same circuit, you can actually get the values at different locations. That is all. I mean, this has nothing to do with microwave engineering, or this is sort of just, logic, basic logic, that how we do it. I mean, I can imagine that this might not strike you if you're not played around with microwave office, or have a sort of an intuition for what's going on. But that's all. There's nothing sophisticated going on here. I need to get to the middle point to be able to put a current meter. I can't do that in this circuit element, which is 180 degrees. Okay.
Sir, if we have arbitrary load on both sides of the transmission line, then can we also, guess where is the current node or antinode?
Yes. So, in fact, why don't we do that right now? It'll just take 2 minutes. See, the circuit is symmetric, right? In fact, if you think about it, this circuit is somewhat less symmetric in the sense that the open end on this side is, a true open, whereas the open end on this side is a small capacitance. So this circuit is actually not truly symmetric. In fact, let's see if we can catch this in the sense that whether the current antinode actually is exactly in the middle or not. So we sort of didn't pay attention to this very carefully, but let's see if we can do that now. See, this was the point where I'd set it to 90 degrees, right? Which is the middle of the transmission line. But let's see if there is I'm going to narrow the range of this variation here and see if I had to guess, I would think that, so let me actually also provide the context, and I think I had mentioned this during my class discussions of how to think about this capacitor here and why it loads the frequency. We had done this, I think I had mentioned this comparison to acoustic resonators. If you have a pipe of a certain length, like a flute or other kinds of things, then that has a resonant frequency. But the boundary condition, when the flute tube ends and it reaches the air, there is an impedance mismatch, but it's not like a perfectly sharp boundary. And so what happens is that it looks like the actual length of the tube is slightly longer than what the physical length is. So this capacitor, because it adds extra capacitance and lowers the frequency, the effect is equivalent to having a longer transmission line, right? If you had a longer transmission line, the frequency would be lower as well. So if I had to guess, I would say that the current antinode might be slightly to the left here, which means for values slightly less than 90 degrees, because the length is longer in this side. So that means the middle point is not going to be at 90, it's going to be slightly over here. I mean, this is my guess. I have not looked at this part in the past before in this way, but let's see if we can see that. Okay. I'm going to put 1 degree step sizes here. That's 90. That's 89. Barely see any change here, but it is coming down. Go to the other side. Yeah, not really. I think the effect is of the extra lengths, I think, is very small, because this is a very, very small capacitor. Let's look at this more carefully. So this is 90. That's 89, 88. Yeah, I barely see any. This looks like it is exactly at the middle. Right. So I hope you understood what I was trying to say here. I was actually trying to motivate the fact that this circuit is actually less symmetric than this circuit, right? It looks identical from either side. So the middle point should be the middle point. But let's quickly put this here. But the general argument of where the current antinode is just from the knowledge of how these kind of transmission line. So this is based on the curves I drew before, right? So there is nothing that just comes from how you think about these resonators. No. Okay, and then I have to put this as a source. And that's it. Now, let me duplicate this measurement and add it for port 2. Okay, so again, you see the resonance at the same. Why is the resonance same? Because we have already adjusted the capacitance of the single port circuit to match. So you see it's peaked at the same value. You also see this a lot more clearly that this is narrower. So the 2-port one was narrower in so sharper resonance, which means lower, higher Q, as we interpreted from these graphs as well. So the same thing is you're seeing in this as well. Now, as regards the whether the node is still in the middle, we can just check that by changing this in the same way. Let me define EL1 equals 90. 180 minus 1. That is the, yeah. So it's still sort of maximum is near 90 only, which is what you would expect maybe. Okay. So yeah, this was basically sort of the final part of the problem. So once you set up for both, you get these curves and you would have to make some observations based on this, which now we already understand that this is narrower. But one interesting thing to note now is let's remember that these plots now are no longer relative plots. This is now giving you on the x-axis a current in milliamps for a port power of 0 dBm. So for example, if I change this power by a factor of 100, let's say I go to minus 20 dBm. So power is minus 20 dBm, so power is 100. That means in linear units, it's a factor of 10. So you'd expect the current to go down by a factor of 10 here. So if I run this, you see that this is now come down here. This is about 67.4 milliamps, whereas here it was 674 milliamps. So exactly factor of 10 as expected. So, but this is an absolute number here. So you can compare, and both the ports are set at 0 dBm earlier. Let me put this back to 0. Remember that the system is still a linear system. It's just that in microwave office, a current measurement is characterized as a nonlinear measurement. It comes under that category because of the way it does the calculation. It doesn't, this requires a slightly more intensive numerical calculation. But the another thing to note is that for the same input power, the peak value of the current is actually the same for both the cases. Now, this was part of the discussion I was going to have with you. But I mean, this is extremely complicated in the sense that, I mean, it's like you really have to think. So this is like super bonus kind of part of the question. And would not have carried a lot of weight in your grade. This is not so obvious that this needs to be the case. The Q factor is different, the power is the same, but there is power leaking out of the other side as well. So you can maybe guess that okay, for the case of the single port resonator now, which has now become more strongly coupled than so it has a broader Q. So generally, when the Q is lower, the current you will get will be less for the same input power. Like the steady state doesn't build up to high enough power, right? So when you have a higher Q system, the energy will build up more. But so you have a reference where the Q is about a factor of 2 smaller, and you get some current in the resonator. The other one has the situation that the power can actually leak out of the other side. So you would somehow expect that the current should have been lower, but it's not lower because the Q is higher. So the two are sort of compensating each other for that. So the higher Q compensates the fact that the power is leaking out of the other case. But these are not really apples to apples comparisons. But that's how you would explain this. I mean, this would have hopefully evolved through a series of discussions and hints. But this is not an easy part of the question at all. This particular part. But the rest of the stuff, at least halfway through, everybody should have gotten through based on what we have discussed in class. And the rest was, whether you are able to think about these things in a logical way. Okay. Right. Any other questions? I think we should stop here. I still have the last question, which anyway was an exploratory thing, but we'll do that in the next session. Yeah, go ahead.
Without doing the detailed calculation, so how can you, guess the effect of the capacitors?
Well, but that's like you're saying that, you have to have some knowledge of what these systems do, right? So in the class, we discussed the effect of the capacitance in the context of a resonator like this. And there we had sort of introduced the idea that, because you see, this LC circuit has a well-defined frequency based on the L and the C. We know that from this particular system. So when we put a series capacitor here between the port, where the main purpose of that capacitor is to couple how much energy from the oscillator can leak into the 50 ohm environment, right? Because this is the only part which is setting the dissipation. So I think we had discussed that, if you don't want to change the L's and the C's, then the Q factor is entirely just given by Q is RC omega plasma, right? So if the resonant frequency is fixed, then, and the 50 ohm environment is fixed, because in microwave, everything is just 50 ohms. So then how can you make some resonator high Q or low Q? The only option you have is to change the ratio of L's and C's, right? Because Q is proportional to capacitance, R is fixed, omega resonance is fixed, because you want some resonator at the fixed. So what it means is that you have to make the capacitor as large as possible and the inductor as small as possible. Now that again is not practical, as we discussed, that you can't make arbitrarily large inductors and capacitors at microwave frequencies. So then the only way you have is to somehow control how much dissipation, and you do that by breaking this direct coupling to the 50 ohm environment and putting in a coupling capacitor here. Now that coupling capacitor has the effect of changing the frequency of the resonator as well. Now if it's small, then it will be a small effect, but it has a finite effect. And we had talked about the fact that you can think that this series capacitance through the source is sort of connected to ground. So it's sort of, it is in parallel. But the real way is, I think it was, I forget now if it was there in one of the problems where we had asked you to compute the effect of a series RC and model it as a parallel RC at one particular frequency. So, there are no simple or some general rules of principle which would give you this. You just have to see the effect of the capacitance and resistor in terms of what its impedance profile looks like. And then you try to match it with a model which you understand. The model which you understand is the simple LCR circuit, because for that you have a formula for Q. So you say, okay, can I now make this look like a effective parallel capacitor? Because then I can just add that capacitor to this and I know that the resonant frequency has shifted. So when you do that calculation, it turns out that the capacitance value is the same value as what you had put in, but now it comes in parallel and adds to this capacitance, shifts the frequency lower. But now the resistor 50 ohm gets transformed, in some ways, there's some R square over R square plus C square. I forget the exact formula. And that is how you get that the Q now increases when you put a capacitance here. The smaller the capacitor, the larger the Q. And the intuition there is that, yes, now if the capacitance is very small, then there is a big impedance between the 50 ohm environment and the resonator. So this energy, whatever you put in, will not leak out so easily. And consequently, it will also not leak in as well, but that's okay. Just control the coupling between the two. And it's equivalent to have changed the impedance of this 50 ohm to some higher value and put that other capacitance in parallel with this particular capacitance. So that's how we had discussed in this class, and the same effect happens for the transmission line resonators as well, because we had discussed this, and also I had pointed this out in the POSAR chapter, that sections of transmission line, like resonating sections of transmission line, can be modeled as equivalent LC circuits, like parallel or series LC circuits, based on how the impedance changes as a function of frequency. So if you have an infinite impedance, then it's clear that looks like a parallel LC circuit, because a parallel LC circuit has an infinite impedance on resonance. If it has a zero impedance, then it looks like a series LC circuit. So that's how we had model, and in the POSAR chapter, they explain how to actually calculate that for a particular case of a length of a transmission line and the characteristic impedance of the transmission line. Okay. Any other questions?
Sir, can you go back to the first problem?
The first problem.
Yeah. Can you show the circuit?
Yeah.
Yeah. So when we from this 2 transmission line, we go to 4 transmission line.
Yes.
So then we have, I mean, here in these 2 transmission lines, we have only one controller, and that automatically decides the Z for the other one. But when we have 4, then we have 2 controllers, right?
Well, no. Ideally, there would be 3, because if you split this
Yes.
into 2, there will be one in the middle here, and there will be one here, and then there will be another one in the middle here. But that's exactly what I said, is that you did not have to split it and do it in such a way. The idea was to understand what is the mid value of this guy in relation to the original 2 impedances you were trying to match. And that we found that it actually has the same value as the square root of the 2 impedance, product of the 2 impedances. So we found that the best mid value, which gave us the maximum bandwidth, was actually equal to the geometric mean of the 2 impedances. So the idea here is that you just extend that idea. So now you say that I have, let me annotate here a second. So you now say that I'm going to treat this as an independent problem, where this is matching 50 ohms to Z mid, right? The Z mid from the previous case, right? So this is now, there's some load resistor here, and I separate this part. So this is now Z mid. Now I can just treat this as an independent problem of something having one section, and I'm going to turn it into 2 sections. And how do I turn it into 2 sections? I need to find a new Z mid, but that new Z mid here is just going to be the square root of 50 into the old Z mid. So I don't need to recalculate anything. So I know the value of Z mid, which means I know the value of the 2 impedance transformers I need on this section. And same way on this side, I have to transform Z mid, the old one, to 20 ohms, which is ZL. So I do the same thing. So that is what I asked you to do. You didn't have to tune all the parameters independently, because that would be crazy. But the fact that the same thing works, for going from 1 to 2 should work for a smaller section of going 1 to 2. At least that's the assumption we are making here. I have not actually looked at whether that gives you the global maximum, but I would guess that it would.
Okay.
Okay. Any last question? Okay. All right. I hope this was somewhat more instructive, and you've understood, at least in the context of what the questions were. And I've tried to identify the places where you have made mistakes, which are all very basic, by the way. I mean, this should have not happened. These more complicated parts of the problem I was not expecting, but I just wanted to see how you think. So please, go back and get yourself familiar more with Microwave Office. Maybe go back and revisit the homeworks also, which you have submitted. I will discuss feedback on the homework in one of the next sessions. And we have to also now figure out when the next session has to be, because some of you, I think several of you, are not available on this weekend because you're traveling. I did want to do at least one of the sessions in person. So I mean, do all of you end classes at like 7:30? I mean, would it be okay if we do like on Thursday or something a little bit late? Maybe you guys have an early dinner by 8:30 and we do like 8:30 to 10:30 or something like that. Does that work for you guys, like say Thursday night? Because during the day, I think it'll be impossible. All of you have very different class schedules, and I will also have other things going on. So that's why I'd initially chosen Saturday, but unfortunately this Saturday didn't work out. And next Saturday and Sunday, I think some people are traveling. So that would be a problem. So if anybody has a problem with this, please raise your hands. Maybe we try 8:30 to 10:30 on this Thursday. Okay, all right. I will send this out on email and we can meet on Thursday. I'll find a room and let you know. Okay, all right.